Thank you very much, Daniel. Very happy that you're still here. So after yesterday's perhaps more technical lecture, today will be more of a mild introduction to relativity and some of the problems that in particular I've been interested in. But before I start, there are two important things that happened today. So the first one is 42 is the sum of 3 cubes. So you should Google it. People just now found the solution to that. So math fact number 1. Number 2, the Event Horizon Telescope folks got the breakthrough prize today. And so I'm very disappointed about that for a reason I'll tell you in a second. But it's, of course, great for relativity as a whole and so on. OK, so all right, so this being general relativity, there's going to be an underlying equation that I'll mostly talk about, which is the Einstein vacuum equation. And of course, general relativity is much richer than just looking at vacuum. You can look at all kinds of matter models. For instance, plasmas that you see on this Event Horizon Telescope picture. But I'm only going to focus on the simplest equation here, which says that the Einstein tensor of a metric G plus a number lambda times G is equal to 0. So that's the Einstein vacuum equation. And here, lambda is a God-given real number. So this is fixed. And then for your favorite choice of lambda, you can try to solve this equation for G, which is a Lorentzian metric, like the Minkowski metric or the de Sitter metric that we discussed yesterday. So let me fix the signature to be mostly pluses on a manifold M of dimension little n. And so you can study these things quite generally, but here, meaning both in this talk and in this room, n is going to be equal to 4. So you have 1 time and 3 spatial dimensions. So what's the Einstein tensor? That's equal to the Ricci tensor of the metric G, which is defined for Lorentzian metrics exactly by the same algebraic expression as for Riemannian metrics, minus 1/2 times the scalar curvature of the metric G times G itself. So it's a symmetric 2 tensor capturing some of the curvature of the space-time. OK, and so I'll now spend some time giving you a number of interesting examples that arise in practice and reality. So actually, before I do that, let me just point out that typically the following formulation of the Einstein vacuum equation is more useful in practice, namely Ricci of G minus lambda times G is equal to 0. And so I'll write down roughly what Ricci is, and you'll see why this is a good formulation. I leave it as an exercise by taking traces that these two formulations are indeed equivalent. OK, so let's look at some examples. And the first one I already mentioned yesterday. So actually, let me split it up even further. The first class of examples will be for the case that lambda is equal to 0. So you would be looking at spacetimes whose Ricci curvature is equal to 0 everywhere. OK, so the first example would be Minkowski space, which I already had mentioned yesterday without giving the name on the board. So that would be the situation in which the spacetime is just the product of R with R3. And the metric I'll denote by G sub 0 to be generalized later. And this is equal to minus dt squared plus dx squared. So it's the Lorentzian analog of the flat Euclidean metric, and as such is also flat. And so geometrically, we discussed also yesterday light cones as some of the most salient feature of Lorentzian metrics. And so if I draw the space-time here, t and x, and you take your favorite point up here, then you can consider the tangent space over this point and draw all the null or light-like vectors whose squared length is equal to 0. And it will always be the same kind of double cone like this. OK, so it's the same thing at every place, t and x. So they're supposed to be exactly the same looking. All right, so this is very simple. And somehow you can think of this quite usefully as the local model of any Lorentzian spacetime. So if you have any Lorentzian metric, you can always find coordinates near a point such that at least at that point itself, the metric looks like this. Okay, and so perhaps another sort of more interesting way of saying something similar is that if you take any spacetime, it doesn't even have to satisfy any equation, and you somehow rescale coordinates, so zoom in further and further, then in the limit that you zoom in all the way, so the metric becomes the Minkowski metric. So it's somehow the sort of a rescaled model of any spacetime you can ever consider. Okay, so this is some of the local model for everything. Now, more interestingly, in terms of the global geometry, the Schwarzschild spacetime, or the Schwarzschild black hole spacetime, which was discovered around 103 years ago by now, I believe. And so this depends on one parameter, m, which in principle can be real valued, but interesting is if it's positive, because it's supposed to be the mass of the black hole. And in this case, the manifold m is, again, a factor of time, and then the exterior of a ball in R3. So you start at 2m and go all the way out to infinity, and then you have a 2-sphere over every point. So the metric in this case is now g sub m, and Michał actually wrote it down in his talk, so here it is again, minus 1 minus 2m over r dt squared plus 1 minus 2m over r to the minus 1 dr squared plus r squared times the metric, the standard metric on the 2-sphere. Okay, so this is, if m is equal to 0, this is actually the same as the Minkowski metric. But if m is positive, then you say that this form of the metric actually breaks down at r equals 0, and also this is a coordinate singularity at r equals 2m. And it's actually the unique family of spherically symmetric solutions of the Einstein vacuum equation, so it's an extremely natural object to consider. And it turns out that already the second most trivial solution of the Einstein vacuum equation describes a black hole, so they're very fundamental objects in the theory. So let me try to justify why you call this a black hole. And to do that, let me just draw the light cones again. So here I have time. In fact, it's going to, okay. So time and radius. And so then there's this place 2m, below which I don't write down the metric here. And so when you're very far, for very large r, the light cones look exactly the same as on Minkowski space, because it's just a 1 over r correction. It becomes very small far out. But as you get closer to the black hole, for instance, there's going to be an interesting radius 3m here, it's very hard to get away from the black hole, but it's very easy to fall further to the black hole. So this light cone here is tilted to the left. When you're exactly at r equals 3m, then in fact it's impossible to move away. And so this would somehow be the light cone. And of course, at this point, I'm already cheating because this metric is not valid anymore at r equals 2m. But as I mentioned, you can write down different coordinates so that actually the metric extends. Just like the polar coordinate singularity at the North Pole, nothing geometric happens. You just switch coordinates to something that's regular there. And it turns out, as an exercise for those of you who get bored, if you take t star equals t plus 2m log r minus 2m, that's a singular coordinate change at this horizon, r equals 2m, then the metric extends smoothly across. Okay, and then you can draw these light cones. Okay, so once you believe me that, then the light cones even further closer to r equals 0 are even more tilted. So they look somewhat like this. Okay, so now why would you call this the spacetime here a black hole spacetime? Well, it's exactly because of this dashed line here, which I already called just now the event horizon. And it has the following feature. So if you start out somewhere in here, and you're either a light particle or a massive observer that can only move along null or time-like directions, so in the interior of these cones, then you can never actually escape outward towards r bigger than 2m. You're bound to stay in this region r less than 2m, and in fact, you're bound to go down to r equals 0 in finite time, where unpleasant things happen to you. And OK, So in other words, this region here is causally, so nothing that happens here can causally affect anything that happens outside. Of course, what happens outside can fall inside, so this causal lack of relationship only goes one way. Okay, but that's why it's a black hole. There's a region from which you cannot possibly escape. So the reason why I was unhappy with this, the black hole, the Event Horizon Telescope getting the prize, they got $3 million for it, for finding the event horizon, and I found it here, but I'm a day late. So, oh well, okay. All right. So, in fact, if you don't mind, there was a talk by a distinguished member of this audience some years ago about the gravitational wave project LIGO and Virgo, and they hadn't discovered anything at the time, but they had already spent $1 billion on it. So this distinguished member said that they should have given the $1 billion to him. He wouldn't have found anything either. But okay. All right, so this is the Schwarzschild black hole. Let me also mention one more feature. At r equals 3m, the following thing can happen. So you can have a light direction, like this one here, which is tangent to r equals 3m. And you can have light rays, the null geodesics, that actually orbit the black hole indefinitely at this radius r equals 3m. And so that means that there is trapping at r equals 3m. And so that's called the photon sphere. And in fact, it turns out that in phase space, so if you look at things microlocally, so T star m, this is in fact normally hyperbolic trapping. So this notion wasn't introduced in the lectures. What instead we had was this Anosov property. And the main difference between Anosov and normally hyperbolic trapping is that in the Anosov picture, you only had one neutral direction, the flow direction, and then you had the stable and the unstable direction. It's the first time I'm doing that dance. And in this normally hyperbolic situation, you can actually have a neutral manifold. So it doesn't have to only be a single direction, but you can have sort of a higher dimensional sort of central manifold. OK, so this is the situation there. I'm not sure who discovered this first in Schwarzschild, but I'm going to give the references in Kerr in just a second. OK, so next up in the scale of complications is the Kerr black hole. And so this lives on essentially the same space-time. Again, you have a mass parameter, but now you also have an angular momentum, which is a non-negative number, and it's bounded by m. So there's a maximal rotation speed for black holes. And you can also, again, write down the metric. I mean, somebody can. I don't know it by heart. And it's some explicit, mildly nasty expression. But the overall picture of the space-time is very similar to this. And again, it turns out that in phase space, in T star m, there again exists a submanifold of positions and momenta such that the null geodesics starting at these positions with that initial momentum orbit the black hole indefinitely without ever escaping off to infinity or falling into the black hole. OK, so you again have, there exists normally hyperbolic trapping. And so, so it's something more better even than that. And so the reference is a paper by Wunsch and Zworsky, and then in the full sub-extremal range by Dyatlov. OK, so, but again, the structure is very similar to the Schwarzschild situation. So these are the spacetimes with lambda equals 0, which again, as I said, should be thought of as models of small regions of a given spacetime. Now, the actual universe, this is going to be very contentious now, but the actual universe has a positive cosmological constant, and the Nobel Prize Committee agrees with me. And the simplest example I again gave yesterday, and it is de Sitter space. Right, so I wrote down the following form of the metric minus d tau squared plus dy squared over tau squared. So I drew this picture here. And this is actually a solution, so this particular one where lambda is equal to 3. So you couldn't put some numerical factor in the denominator to make it another constant if you wish. So that's de Sitter space, and we in fact studied a subset of this by taking our favorite point at infinity, sort of at future infinity, and looking at the backwards light cone from it. And then remember that we could localize the study of wave equations to such a patch here. And in fact, we blew it up because this is too singular at this cone tip. And then we arrived at the following picture. So here I have a coordinate x, which was equal to y over tau. And then you have this function tau, which we're thinking of e to the minus some time function t star. Okay, so time goes to infinity as you approach this ideal boundary here. And so in this picture, you in fact again have a similar situation as in this event horizon here, as follows. Right, so here the horizon is at x equals 1. Up here it would lie at y equals tau. But in this picture you have the same, you can run the same argument. So suppose I'm only interested in understanding what happens in this triangular region here of my de Sitter space, or the region down here. Then all you need to know, so in other words, what you do not need to know is what happens outside of this region, because anything happening here, so if you have a solution of the wave equation with initial data somehow supported here, the solution will have support only in the causal future like this, so it will never actually reach me over here. Okay, so in other words, the fact that I'm drawing this light cone here means that these dashed lines here are, again, a horizon of the same type as the event horizon in the black hole spacetime. Everything that happens outside of this horizon cannot possibly affect anything inside of the horizon. Okay, and so in this case, it's called the cosmological horizon. There's no black hole. But geometrically and in fact analytically, it's the same thing. Okay. So that's de Sitter space. And the final one I'm going to introduce. So somehow de Sitter space is the analog of Minkowski space. It's some of the maximally symmetric solution with positive cosmological constant. And now the analog of Schwarzschild spacetime would be naturally called Schwarzschild de Sitter spacetime. And then I'll let you off the hook with these examples. So this, again, depends on the mass parameter m, which is positive. In fact, it cannot be too big compared to lambda, but OK. And the metric in this case, let me just call it gm again, has a very similar form. Just for your amusement, it's 1 minus 2m over r minus this extra term, lambda r squared over 3. But otherwise, it looks the same as the Schwarzschild metric. So in particular, it's a generalization of the Schwarzschild metric, because if you formally put lambda equals 0, you get back to the Schwarzschild situation. Also, incidentally, if you set m equals to 0, so you have a Schwarzschild de Sitter spacetime with no black hole in it, mass 0, then this is actually a local coordinate expression for de Sitter space in some funny coordinate system. OK, so they're all interrelated. And in fact, the geometric or physical nature or structure of the spacetime is a combination of de Sitter space and Schwarzschild spacetime. And so the picture that I'm going to draw now is necessarily slightly different from the ones I drew previously. So it's what's called a Penrose diagram. And I'm going to draw it quickly and then explain what's going on. So roughly speaking, the radial coordinate goes like this. Then you have a time coordinate, or rather some slightly modified one, as in Schwarzschild. Then you have the two horizons, the one that you know from de Sitter space, the cosmological horizon, out here. And then you have the event horizon that you know from the Schwarzschild spacetime over here. And it roughly lies at r equals 2m. And the cosmological horizon is roughly at, I think, 3. Perhaps it's square root of 3 over lambda. Don't quote me on that. OK, so if lambda is very small, this cosmological horizon is huge. In our actual universe, it's many, many billions of light years out. OK, so in this diagram, let me draw it slightly more fully here. In this diagram, what happens is that light rays, so null geodesics, just like in the picture up there or in the Minkowski picture, move at exactly 45-degree angles. Okay? So the cosmological horizon here is at 45 degrees, meaning that if something happens out here, so if, for instance, Michał and Antti Andras shake hands here, the resulting explosion, the signal will never reach me in the domain that I'm interested in. Okay. Unfortunately, if Michał was out here, so Antti Andras seems like a nuisance anyway, but if Michał was out here, unfortunately, he would never be able to communicate with me either, which would really be a bummer. Okay, so that's the Penrose diagram for Schwarzschild de Sitter space. And then there's also the Kerr cousin, which is called Kerr de Sitter, which again has an extra parameter of angular momentum. And in this case, so in these cases, again, you have the same kind of normally hyperbolic trapping. And so this was, I think, first proved by Bashi, and then larger parameter range by Dyatlov. OK, so very good. Any questions about the geometry so far? All right, so if you look at these spacetimes, at least the metrics I wrote down explicitly, they all have a very particular feature. Namely, they're time independent, right? The metrics do not depend on the parameter t in any way. So it would be interesting to get some dynamics into the picture. And so the way that one typically does this is by considering the initial value problem for the Einstein equation. So now we're getting closer to the analytic issues. So how do you actually solve this Einstein vacuum equation on the top left? OK, so to give you just a quick feel for what this Einstein vacuum equation looks like, here's a rough expression for the Ricci tensor of a metric G. So I'm going to use the so-called Einstein summation convention, which means you sum over K and L when they're repeated. And so you take these second derivatives of the metric coefficients G sub ij, and then there are some extra terms of some similar form. And then there are some first-order terms, nonlinear. Okay, and I'm going to tell you roughly what these extra terms here look like. What I want you to mainly notice is that this, what will end up being the main term, looks like the wave operator of the metric G applied to the metric coefficients Gij. Okay, so modulo understanding what happens with these extra terms here, the Ricci, so the Einstein vacuum equation is something like a quasi-linear wave equation. Right? Quasi-linear because even the leading order derivatives depend on the unknown G itself. OK, so right. So the theorem then about the initial value problem is the following. So it goes back many decades to Choquet-Bruhat in 52 or 53. And it goes like this. So it works for any fixed cosmological constant lambda. And what you're given is the following, which I want you to notice looks slightly funny if you're used to the usual theory of initial value problems for wave equations. So you're given a three-dimensional manifold sigma and a Riemannian metric gamma on sigma. And you're also given a K, which is a smooth symmetric 2 tensor. Let's just say everything smooth, a symmetric 2 tensor on sigma. And what you, and very importantly, they satisfy certain compatibility conditions called the constraint equations. And I'll tell you in a second what they are. And what you want to find, given these initial data, so here they are. What you want to find is a space-time mg. So this is now a 4-dimensional space-time satisfying the Einstein vacuum equation. So Ricci of g minus lambda g is equal to 0, in which sigma sits as an embedded hypersurface. Okay, so you have an embedding, let's call it iota from sigma into m, such that the initial data, these geometric initial data, are attained as follows. Namely, the Riemannian metric gamma is the pullback, or the restriction, of your metric G to this hypersurface. And K is the second fundamental form of this hypersurface, or the image of it, with respect to the metric G. Okay, so the metric itself is somehow just restricting. And the second fundamental form is given by taking one derivative of the metric. So somehow this looks like Cauchy data for an ordinary wave equation. Okay, so notice that I didn't say there exists, the theorem is not to find something, but there exists something. So Choquet-Bourgeat found it. Okay, so notice that I did not say that there is a unique solution. And this is, in fact, one of the main difficulties when dealing with the Einstein equation. Namely, suppose you have a diffeomorphism phi on your space-time M, which is equal to equal to the identity near the initial surface, but perhaps something else outside. Then pulling back the solution G by this diffeomorphism gives you, again, a Ricci, a metric satisfying this Einstein vacuum equation. It also has the same initial data, but generally will be pointwise a different symmetric true tensor, different metric. So this also solves the initial value problem. And so the uniqueness claim in this theorem is basically that any two solutions of this initial value problem are related by pulling one back by a diffeomorphism and getting the other. So this is some of the only non-uniqueness you have. So let me just say it informally, uniqueness modulo these diffeos. Okay, so just to slowly connect this to what we talked about yesterday, namely nonlinear waves, let me be more honest now about what to do with Ricci versus an honest nonlinear wave equation. Okay, so let me just sketch the main idea of the proof as follows. So let's just take lambda to be equal to 0, just so I have to write less. A natural first guess as to what the manifold, the space-time looks like locally is just you take a small interval in T cross sigma. That's definitely something pretty reasonable. And you want to solve Ricci of G equals 0, which I said is difficult because it's not actually a wave operator. And we make the problem even harder by imposing some extra conditions. So W of G, which is going to be a 1 form, just meaning 4 different conditions depending on G and its first derivatives, equals 0. And so naively speaking, you have 4 extra conditions, whereas a diffeomorphism somehow has 4 different components. And imposing these 4 conditions basically pins down all the components. So you somehow kill off the diffeomorphism invariance by imposing these extra 4 conditions. Okay. So what does this 1 form typically look like? So typically, W of G is, there are various ways you can write it down. I don't know what, for this audience, the preferred way would be. One thing you could do is you take the connection of your metric G, you subtract off the connection of your favorite fixed metric on the spacetime M, and you take the trace of this. So this gives you 1 form. In local coordinates, this is some difference of Christoffel symbols. This is also basically the same as, I think it's called the stress tensor for a wave map. So you're asking whether the identity map from the manifold M, G to the manifold M, G naught is a wave map. Okay, so let me just write that down. So W of G is equal to 0 if and only if the identity map from Mg into Mg naught is a wave map. Okay, so obviously you can do many more general things, but let's leave it at that. Okay, so now you make your problem harder, and then you make it into a different problem altogether by looking at the reduced Einstein vacuum equation, which is the following. So you look at Ricci of G minus delta G star. This is the symmetric gradient of this 1 form, W of G. Okay, so formally, this, so I want to solve this is equal to 0. This is a second order operator. This one here, first order operator applied to another first order operator. So this is second order. And it turns out that this extra term up here, this term here, is exactly equal to plus minus, I'm not keeping track of the signs, exactly equal to this extra term up to lower order terms that I'm writing down here. So in other words, adding this extra term exactly kills off the non-wave equation part of my expression for Ricci of G up there. Okay, so in other words, this now is a quasi-linear wave equation. For the unknown G. Okay, but it's a completely different equation, so I have to justify why solving this equation has anything to do with solving the Einstein vacuum equation. So let's do that. The steps now to find the solution of this initial value problem are then as follows. First, you start with your symmetric two tensors gamma and k. So remember, these are locally 3x3 matrices, right? They're symmetric two tensors on the three-dimensional manifold sigma. And out of those, you cook up honest Cauchy data for a wave equation. So these two are now symmetric two tensors on the manifold M on the space-time, so they're 4x4 matrices. And you're going to construct them at t equals 0, so at sigma itself. And how do you do this? Well, you arrange that they actually, a metric with these Cauchy data has these geometric Cauchy data here. So gamma is equal to the pullback of G0. Oh, this is bad notation. Okay, let's call it G upper 0, G upper 1. Sorry about that. Okay, so you want to ensure that these, the initial metric here pulls back to give you the Riemannian metric, and that the second fundamental form here is equal indeed to the second fundamental form of the metric with these Cauchy data. So let's say G0 plus t times G1 of sigma. Notice that because the second fundamental form requires you to just calculate one derivative of the metric, knowing the metric and its first time derivative is enough to verify whether the second fundamental form gives you what you want. And the last thing you want to ensure is that the gauge condition is also satisfied. So if you take a metric with the same one jet here, and you compute the gauge condition, so this one form, it's supposed to be equal to 0 at time t equals 0. So this is some of the main step. But because you're passing from 3x3 to 4x4 matrices, you imagine you have sort of 4 extra degrees of freedom to play with. So you should be able to arrange these extra 4 conditions here. OK, so this is an exercise in algebra. The second step is now to solve this PDE. So solve the reduced Einstein vacuum equation with these initial data. And so the metric G already satisfies the initial conditions, of course. But it satisfies this reduced equation, not the Einstein equation itself. So what's going on here is the following. So it turns out that the constraint equations, which I forgot to mention, I'll do that in a minute, they actually imply that once you have a solution of this equation, this gauge condition is automatically satisfied to the next order as well. So its time derivative is equal to 0 at t equals 0. So let me just quickly say what the constraint equations are. Right, you're trying to find a metric on a 4-dimensional space-time, so the metric G, which satisfies a curvature equation. And so then from basic Riemannian geometry or semi-Riemannian geometry, you remember that then the induced metric and the second fundamental form satisfy certain compatibility conditions, the Gauss-Kodazzi equations. And the constraint equations are exactly the Gauss-Kodazzi equations for gamma and k. OK, so, and again, this is something you have to take for granted now, but it's a simple calculation. All right, and the final step is then, so now you have this gauge one form W of G, and we're now going to show that not only its Cauchy data vanish, but in fact it vanishes everywhere. And so that's the last step, which uses the so-called second Bianchi identity, which again you might know from Riemannian geometry as the statement that the divergence of the Einstein tensor of any metric is always equal to 0. OK, so remember that the Einstein tensor was equal to take the Ricci tensor and subtract from it 1/2 times the scalar curvature times the metric. So let me codify this as G sub G, where this takes a symmetric 2 tensor and subtracts 1/2 times its trace. Okay, so this is the second Bianchi identity. It's again an algebraic identity really about G, and it's up to second derivatives. Okay, so if you use this identity now and apply it to the reduced Einstein vacuum equation, then the Ricci tensor disappears. So you get that the divergence of this capital G applied to the symmetric gradient delta star of W of G is equal to 0. So you automatically get this extra equation for W of G. This seems like a miracle, but perhaps to give peace to your mind, it turns out that the second Bianchi identity is actually, in a certain sense, a consequence of the diffeomorphism invariance of the Ricci tensor. Somehow it all fits nicely together. In any case, you get this new PDE for W of G, homogeneous PDE, and it turns out that this operator here is equal to 1/2 times the wave operator of the metric G, perhaps plus some lower order terms. Okay, but at this point you're done because you have a solution of a homogeneous wave equation whose Cauchy data both vanish. And so then by uniqueness of solutions for wave equations, you get to conclude that this W of G is identically 0 everywhere. And therefore, by plugging this into the reduced Einstein vacuum equation, you also deduce that Ricci of G is equal to 0 as you wanted. Okay, so this particular way of putting the gauge condition in sort of in this geometric fashion, I believe goes back to de Turk. It's called the de Turk trick usually. Was very useful to simplify the proof of local existence for the Ricci flow as well. Okay, but Choquet-Bruhat's original argument is basically this, just written slightly differently. Okay, so this is how you reduce the problem of solving the Einstein vacuum equation to a problem of solving a quasi-linear wave equation, which we talked about yesterday. So ideally now we should be able to solve a ton of Einstein vacuum equations for all kinds of spacetimes. So let's do exactly that. I suppose this is 3. So I should point out that relativity is a much bigger topic than what I'm indicating here. This is just close to my personal heart. So there are lots of things, for instance, in Riemannian geometry or geometric analysis about trying to solve these constraint equations in large generality or understanding singularity formation. And there are lots of people in this room who have contributed majorly to this. But I'm the speaker, so I get to decide what to talk about. OK, so stability of Minkowski space is the following rough setup. So you take as your initial surface R3, and the initial data are gamma and k, and they're the following. So the zeroth thing you would try to do is to say, well, I want the initial data to be close to the Euclidean metric on R3. But it turns out it's useful to keep track of one more term in the expansion. So remember, this was the Schwarzschild metric, which is up there. So there's this extra 1 over r correction term. OK, so you would like that the Riemannian metric on R3 minus the Schwarzschild metric is less than r, some small constant times r to the -1 minus some positive number alpha when r is big. And you also want this mass to be very small. Close to r equals, so close to the origin, you just want it to be close to the Euclidean metric. I can write that down. And the second fundamental form, you just want to be decaying like r to the -2 minus alpha everywhere. So it decays at one rate faster. It's again a typical thing for wave equations on Minkowski space. OK, so here alpha is positive. And of course, in reality, you need to impose these kinds of decay conditions for not just the coefficients themselves, but also for a lot of derivatives. So the same thing for derivatives like dxi or xj dxk, and take 1,000 of them just to be on the safe side. OK. So then under these assumptions, the theorem on the stability of Minkowski space says the So that's by now a pretty old theorem. So in roughly this generality, it was proved by Christodoulou and Kleinerman. It was actually preceded by work by Helmut Friedrich for a very special class, however, of initial data. Then there was a different proof given by Lindblad and Rodnyansky in the last decade. And there are many other sort of variations on either one of those proofs. And so Andras and I also gave one such variation, which very well fits into the theme of the geometric microlocal analysis. So, but one step at a time, the theorem states that there exists a geodesically complete solution of the initial value problem. So G, which is Ricci flat, on R4, such that it decays towards the Minkowski metric sort of component by component. Okay, so this decays to 0 in space and time. So it's bounded by 1 plus t plus r to the minus 1. Perhaps there's some logarithm or something like that. But it decays in all space and time directions to the Minkowski metric. So this is the very, very rough version. Okay. And sort of in the context of this conference, what Andras and I proved is the following. If the initial data gamma and k are in addition polyhomogeneous, so Rafe spelled it out for you. I'm just going to abbreviate it, PHG, polyhomogeneous, on the compactification of R3 to a ball. So here's the compactification. I'm just going to draw it as a one-dimensional thing, meaning that you have a Taylor expansion or generalized Taylor expansion in terms of powers of R inverse or logarithm of R. Then we show that G is also polyhomogeneous on a suitable compactification of R4 to a manifold with corners. I have 15 more minutes, is that right? Okay. So I'm not going to dwell too much on this, but roughly speaking, the compactification looks like this. Okay, so here you have your initial surface, R3 compactified, so that's sigma. And then I mentioned many times that some of the most interesting information is contained in the outgoing, in light cones or light rays. And null infinity is sort of the endpoints at infinity of null geodesics in the space-time. Okay, so this is null infinity. And then you also have time-like infinity, which are the endpoints of time-like geodesics. Like I am going to end up at some point up here. And then space-like infinity is the rest, which is endpoints of space-like geodesics. Okay, so there is some nice compactification, and the solution has a product-type expansion at all boundary hypersurfaces. And so notice that these x, dx kinds of vector fields are exactly the conormal vector fields or B vector fields on the compactification of R3 to a ball. All right, so now because I'm shorter on time than I thought, the next one up, following my list of spacetimes, would be the stability of the Kerr metric. So that's the problem of usually just called Kerr stability. And that's still open, though there has been some progress by Kleinerman and Seftel in a special symmetry class. And there are also works on the linearized problem, so where you don't solve the nonlinear Einstein equation, but the linearization thereof. And so there was a paper recently by Anderson, Beckdahl, Blue, and Ma. Then Dietrich Hafner is going to talk next Wednesday, I believe, about our recent work on this. And then Dafermos, Holzegel, and Rodnyansky also have results in this direction. And in fact, the Kerr spacetime, even though I'm going to talk the least about it, is the one that has received the most attention in the literature. And so there are many, many works that study, for instance, the scalar wave equation or Maxwell on Kerr. And so there's a long list of names, including some of these people here. And Tataru, for instance, proved optimal decay rates. Tohaneanu. Yeah, so there's a long history, and I'm going to stop at some point writing down names. Donninger, Schlag and Soffer. Felix Finster, and smaller. And apologies to anybody who I'm not mentioning, like Jacob Sturvins. OK, so there's all I'm saying is there's a very big literature on this. But the nonlinear stability result is still elusive. OK, so let's then talk about things that have been proved again. And that takes place in the positive cosmological constant setting. So one thing I would like you to notice already in the Minkowski theorem is that the decay rate towards the final states, or towards the trivial solution, is only polynomial. It's just 1 over t, basically. And in fact, for instance, the optimal decay rates proved by Tataru on Kerr say something like t to the minus 3 decay, and that's actually sharp. So you do not have exponential decay that I talked about yesterday on de Sitter space. And so that's somehow a feature of these spacetimes with vanishing cosmological constant. So if lambda is positive, the situation in terms of decay is much better. And so there we have the following theorem, which is the analog of the Kerr stability problem, but for Kerr de Sitter black holes. And so that's the theorem. And it states the following. So I have the Penrose diagram up there. That's also the diagram for Kerr de Sitter. So let me just redraw it here, slightly different fashion. OK, so again, you have the event and cosmological horizon here and here. And notice that I sneakily drew it in a blown-up fashion, right? So this is some of the same picture that I drew yesterday a few times for the blown-up de Sitter space. And the reason is that this way it actually looks exactly like the space on which we did analysis yesterday. And it turns out that indeed, again, you will have radial points here, radial points here. You do analysis in the B cotangent bundle. The main extra feature here is that you have this trapped region for which you use these estimates by Wunsch, Zworsky, Dyatlov, and so on. But at least in the horizons, the analysis is exactly like what I sketched yesterday. OK, so what's the theorem in this case? You're now given, again, initial data gamma and k, which are close to, in some high regularity norm, like Sobolev space of 21 derivatives or something, close to the initial data, so close to the data of a Kerr de Sitter black hole. So let's call it GKDS with mass m initial and a initial. And we only study the case when the angular momentum is extremely small, so slowly rotating black holes. Then we prove that there exists a solution of the Einstein-Bakström equation on the domain omega. So Ricci of g minus lambda g is equal to 0. And black hole parameters m final and a final such that the metric g is actually equal to the Kerr de Sitter metric with these parameters, the final parameters, plus something that's exponentially decaying. So yesterday I called it u-twiddle, now it's g-twiddle. And g-twiddle is bounded by some constant times e to the minus alpha t star, where alpha is some positive number. OK, so for large times, the only degree of freedom that you have when you perturb these Kerr de Sitter black holes is just wiggling the black hole parameters a little bit. And anything else, like what LIGO would measure gravitational waves, that's contained in g-twiddle, decay exponentially with time. OK, so in Kerr, the expectation is that you only have polynomial decay. So g-twiddle decays like t to the minus 2 or 3, something like that. OK, so I still have 10 minutes. So rather than say something about the proof of this, let me simplify the situation and talk about the spacetime, which we already discussed yesterday anyway. And so that would be 2 prime, let's say, which is, again, a theorem. It's also in that same paper, but it's much older than that. So it's sort of a special case of a result by Friedrich, which was generalized by Anderson, Ringström. And so that's the statement about the stability of de Sitter space, or rather, I'm only going to talk about the static patch of de Sitter space, which now mysteriously disappeared from the board, but it's the, this one here that I drew before. So you had the coordinate x and tau equals e to the minus t star. Okay. So this is now de Sitter space. And again, you have the same theorem. So let me just make it very brief. So gamma and k close to the data of de Sitter space, so of de Sitter space on the surface sigma, right? Which yesterday I believe I said was x is less than equal to 2 at time t star equals 0, let's say. Then you again have a global solution G. So then there exists G on omega, which satisfies the Einstein vacuum equation. But this time, there's no interesting degrees of freedom asymptotically. So the metric G minus the de Sitter metric, so let's call it G de Sitter, just decays exponentially, period. Okay, so there's no parameters somehow at late times that you need to keep track of. So the solution just decays to the de Sitter metric in this case. Turns out actually that the stability of all of de Sitter space, where you don't only look at this blown up patch here, is more subtle than that. So this theorem applies to every single backwards light cone separately, but they don't somehow fit together in one single neat way. So the asymptotic behavior globally is actually not that of de Sitter space, but of something more general. So it's quite a subtle issue. But yeah, locally here, it just converges back to de Sitter space. All right, so I have 7 minutes left. And so that suffices, of course, for the detailed proof. And so we just follow this strategy of this de Turk trick. So you solve the reduced Einstein vacuum equation. So let's give it a name now. P of G is equal to this reach of G minus lambda minus this extra gauge term, symmetric gradient of W of G is equal to 0. And then we also have to contend with the initial conditions, which over there I called G0 and G1. And by the way, a natural choice here, because we're considering perturbations of a particular spacetime, the de Sitter spacetime, is that this background metric with which we compare things is the de Sitter metric. But many choices are OK. OK, so this is what you want to solve. It's a quasi-linear wave equation of a similar kind that we discussed yesterday. So our strategy is to use an iteration scheme in which we solve a linearized equation globally at each step. So what this boils down to is that we have to show the following sort of consistency problem. So suppose I already knew that my solution had the claimed form. So suppose you have a metric G, or rather an iterate gk in the iteration scheme, which is the de Sitter metric plus an error term, which is exponentially decaying. So yesterday we used these kinds of B Sobolev spaces, but just imagine that it means exponentially decaying. Forget about regularity. OK, so for such metrics that we have the following mapping properties of the linearization of our wave equation. So we need to show that if we linearize our nonlinear equation at such a metric G, and we try to solve it, well, so what are we trying to solve in any case? Turns out that this is equal to 1/2, or let's drop factors. It's the wave operator associated with the metric G acting on symmetric 2 tensors, because we're solving for a metric, plus some lower order terms. And that's what we want to invert. So find the solution operator for. And what we want to show is that this operator here maps whatever error terms we might have on the right-hand side. So they're going to be exponentially decaying, perhaps of regularity s minus 1. I'm just copying basically what I had yesterday. That they map this into a space of the same decay. Okay, so here, again, remember alpha is some perhaps small positive number. Yesterday, in the situation for the scalar wave equation, we actually always got a constant asymptotic term here. But if we get lucky, this doesn't happen. So why would this kind of statement be sufficient to conclude the proof, morally? Because then you could just run this iteration scheme that I said yesterday. You just first solve the linearized linear wave equation, where you linearize around the de Sitter metric. You get as a solution something that decays exponentially at some fixed rate. So that's your next guess. You linearize around that again. You solve away the error terms, and you just keep going. And everything remains consistent in the sense whatever you plug in, what kind of metric decay you have, is what the solution operator in the next step spits out for you again. So this is somehow, for people who like bootstraps, that's somehow the analog, in a way, of sort of the bootstrap assumptions being somewhat consistent. OK, so right. So I already told you yesterday also. So in principle, I could just actually leave this room now and just have somebody on the board and do the proof for me, because it's just like yesterday. So what suffices to be done is to compute the resonances for the simplest model problem. So compute resonances of of the operator. You linearize the equation around the de Sitter metric, G sub ds. Right? Remember that in the solvability theory, what we did was two steps. The first step was to actually have some regularity theory, but where we don't care about having decay. In fact, we were OK with having serious exponential growth in the solution, but strong control on the regularity. And then the next step, we just use the model operator and the asymptotics that its solutions have to iteratively improve on the decay that we get until we reach something like exponential decay, which is good enough for our iteration scheme. For instance, you can square exponentially decaying things and not get in trouble. OK, so we have to compute resonances for this operator. And I'm going to compute them on the blackboard now. So here's the complex plane in sigma. And there's a gap here of size alpha, and the resonances are down here. So that would be the ideal situation. But if this were the case, then we would be done proving this theorem. So using what I did yesterday. So apologies to those who couldn't come yesterday. That part you have to read up. OK, so that would be the ideal situation. Unfortunately, it's not quite so simple. So the reality is a little bit less pleasant. So it turns out that there actually do exist some resonances in the upper half plane, and then God knows what down here. But there are only finitely many. So the reality is that there do exist exponentially growing resonance states. Let's just say briefly resonances. But it turns out that they are they don't have a physical meaning, so it's not somehow the space-time itself goes bad. But really what happens is that they correspond to, so they're of the following form. Right, so t tau to the I sigma j, the kinds of expression which we had yesterday as well. So the particular solutions that you may encounter actually have a very specific form, namely they're Lie derivatives of your metric, of the de Sitter metric along a certain vector field. And so they somehow morally correspond to infinitesimal changes of coordinates. Okay, so you do get some exponential growth, but it just corresponds to your coordinate system somehow going awry. So what you do is you change the gauge condition a little bit. So that would take another blackboard to do. But you change the gauge condition a little bit to make sure that you do not get these exponentially growing contributions. So there's some scheme to do that. Should also point out that so in de Sitter space, this asymptotic behavior is very easy to get. In Kerr de Sitter, you have to work quite a bit harder, and there are actually extremely precise results for in particular, the scalar wave equation. So let me just end by mentioning those, which, as far as I know, really sort of kick-started the scattering theory and microlocal analysis approach sort of for these Kerr de Sitter things. So this is some paper from Saverio and Zworsky from the late 90s. And then there are a whole bunch of papers by a variety of authors, which I write down without any order. So Vashi and Dyatlov. And then Wunsch and Zworsky I already mentioned. I myself also had some contributions. So yeah, so this is some of the conclusion. All right, thank you very much. Sorry?
Can you make sense of this optimal decay rate to tyrate?
In what?
Using microwave.
Well, so in fact, his approach was also spectral theoretic, where you can control, I mean, he's the person to answer this better, of course, but where you control the resolvent very carefully at, in particular, at 0 frequency. And so if you get sort of optimal regularity of the resolvent there, by the Fourier transform, this translates into the correct decay rate. Of course, I mean, this in principle only shows that you have at least t to the minus 3, that you have exactly t to the minus 3. I'm actually not quite sure right now. Yeah, I would have to think about the reference for that. Yeah. Do you know who did that? Yeah, OK. Anyway, so apparently it's true. But yeah, so this is already sort of in a very similar spirit, spectral theoretic. Yeah.
Yes, for the Kerr model, you said that there is a trap set,
Mm-hmm.
which is normally hyperbolic. Is it possible to compute explicitly the resonances for that model?
So Simon Dyatlov has some papers on the Kerr-de-Sitter context in which you actually see the resonances in the wave expansion. So for Kerr, because you only have polynomial decay, it's more hard to actually see them, even though there are also some results in that direction. And so what one can do in this case, what Simon has done, is to give sort of precise asymptotic formula. So as formulae, so as the real part of the resonance goes off to infinity, you get very precise expansions of the resonance in terms of you know, the overtone and the black hole parameters and so on. But explicitly, I mean, no. But you can, yeah.
The dynamics on the trap set is integrable.
Yeah, so that's exactly what's used to get these kinds of precise things with you know, quantum normal forms and such things. So that's exactly what's used. I don't think without complete integrability, there's much hope to actually locate them. You can still prove counting laws for them. Again, Simon did that. Everything Simon. But yeah, precise information you cannot get otherwise, I think.